All right, what's up, team? From the previous video, we have seen that the valence bond theory fails to explain how atoms form bond in the molecules, right? So we need a new theory to help valence bond theory explain how this works. We call this theory a hybridization theory. All right, I'm going to start with the basic here. So hybridization theory is a little complicated, okay? But we're going to keep things simple here. All right, let's watch right here. So I have a horse and a bird. Let's say if I can mix these two up, what animal do I get? Well, a Pegasus, right? Looks like a horse and a bird. Now, one more time. I have a lion and an eagle. Mix them up. What do I get? If you watch have read Harry Potter, well, we got a griffin, hey, or hippogriff in Harry Potter. One more. If I can mix Chris Pine and Bradley Cooper, who do I get? Oh, come on. Can you see that? Isn't it obvious? Hey! So what I want to say is the offspring of the hybrid possesses characteristic of the parents. Pegasus looks like half horse, half bird. Griffin looks like half eagles, half lion. And me, if you look on my right, I look like Bradley Cooper. If you look on my left, I look just like Chris Pine. Hybridization theory explains exactly like that. Carbon is not suitable to form four bonds. This is what carbon is going to do. Carbon is going to take 2s orbital, 2p, 2p, 2p. That's a valence shell right here. This is a valence shell of carbon. Mix them up. Carbon will get 4 new identical orbitals. They look exactly the same. Okay. We have the word for it. We call degenerate, which means equal in energy. They look exactly the same, identical. All right. So mix S, P, P, and P. Use 4 orbitals. You get 4 orbitals coming out. All right. Now we have to name this orbital so we can communicate. Since these orbitals come from one S orbital and 3 P's orbital, let's call it sp3. Keep things simple. Okay. So these are sp3 orbitals, and since they have the same energy, look at energy diagram right here. I have a little energy diagram. They are on same energy level. See that? Now. There are 4 electrons right here in a carbon atom, right? 4 valence electrons. So this electron is going to be, hey, these orbitals are exactly the same energy. Why do we stay together right here? This is too tight. If you still remember that electrons are really smelly. They don't like to be nearby each other, right? They try to stay away from one another as possible. So we're gonna take all these 4 electrons and line them up in here. According to Hans rule, we're going to go up, 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 and up. Remember that? Look at this. What happened? Hybridized carbon have 4 new half-field orbitals. See that? Before hybridization, no, only 2 half-field. But after hybridization, 4 half-field orbitals. And that's exactly what this carbon wants. Want to form 4 bonds, 4 half-field orbitals. So each hydrogen can overlap with this orbital. Ta-da! All right. This we use hybridization theory to explain how carbon form bonds. Now, not done yet. How do we explain tetrahedral though? Right? Because we know the geometry of methane is tetrahedral. Well, we're going to use a different theory, and it's the old one: valence shell, electron pair, repulsion of Vesper theory. It says that the molecules will adopt a geometry or structure that minimize electron repulsion. If you have 2 electrons group, the best structure that minimize electron repulsion is linear. If you have 3, that's trigonoplanar, right? In this case, carbon have 4 electron groups. The best structure, when I ask what's the best structure, when I ask students this, some students will say, "Oh, square planar. Put them far away from one another." Yes, it's correct, but you look at this as a 2D, 2-dimensional. Does it make sense? For square planar, the angle between orbital is only 90 degrees. But we forgot that this is a 3D. This guy can do better than that. Take a look. Carbon will twist 2 lobes at the top, and they're gonna line up perfectly. It's supposed to line up. I mean, because if I do that, you can't really see it. So I kind of like make them staggered a little. Okay, they're gonna line up perfectly on look like a z-axis right there, and that's actually the tetrahedral, right? And guess what? They all all CH bonds are identical. 109.5 better than 90 degrees for the square planar, right? The angle 109.5 and they are identical. Same bond energy, same bond length. And here's how we use hybridization to explain how atoms form bond in the molecules. Okay. All right. There are quite a lot going on in here. Let's review what we just learned. Okay. First of all, why is carbon in methane? This guy right here, sp3 hybridized. Well, without hybridization, right? Without hybridization, carbon, the unhybridized carbon is not suitable to form bonds. Look at it right there, right? Carbon want to form 4 bonds. It got only 2 half-fill. This guy needs to have 4 half-fill orbitals, not suitable to form bonds. After hybridization, carbon actually have 4 half-fill orbitals. Okay? And why is sp3? Well, this guy needs 4 half-fills, so for each hydrogen. So you need to take 1, 2, 3, and 4. So 4 orbital total. So S is orbital, S is 1 orbital, and P, 3p is orbital. Like that. All right. Now, next one. Why is the molecular geometry of methane is tetrahedral? Well, the best geometry that minimizes electron repulsion is tetrahedral. Right? So because carbon got 4 electron groups, the best structure is going to be tetrahedral. Without the hybridization theory, we probably think that carbon formed that geometry. I don't even know what that is. Okay? All right, one more time. So water is also, the oxygen in water is also sp3 hybridized. Why though? Can you explain it? Here's the explanation. Use the hybridization theory. Okay. So now oxygen want to form 2 bonds with each hydrogen. No, sorry, with the 2 hydrogens. All right. So two bonds total. How many half-fill orbital does this oxygen need? Yep, 2. Right. So oxygen gonna need 2 half-fill orbitals. Yep, that's for the 2 hydrogens. And also oxygen also need 2 empty orbitals for these 2 lone pairs. Oh, lone pairs are electrons, right? So they need somewhere to go to. They need orbital for the lone pair. So oxygen will need 2 more empty orbitals for the lone pair. So we have to count lone pair too. So how many orbitals does oxygen need total? 1, 2, 3, and 4. So this oxygen will need 4 new orbitals. Well, hybridization right there. So S orbital, P, P, and P. So sp3. You know that? So oxygen will take S orbital, P, P, and P, mix them up to get 4 new orbitals. They look exactly the same, called sp3. All right. Now, the electrons right here. Oh, this is too tight right here. Too tight right here. Spread them out in here. They already have the same energy. So I'm gonna go. How many electrons are there? 1, 2, 3, 4, 5, 6. So 6 electrons. I'm gonna go up, 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 up. All right. Full now. Go back to the first one. Down and down. That's 6 total. Look at that. What we have here. So we have 2 half-filled orbital for the 2 hydrogens, and that's the lone pair. That's an empty orbital for the lone pair. All right. So basically, use a valence shell electron pair repulsion. The best geometry is tetrahedral, right? And 2 half-filled, 2 empty orbital. Yeah, 2 half-filled, 2 empty orbital. So we get each hydrogen will overlap with the half-filled orbitals, and these 2 are the lone pair. Okay. Oh, by the way, so what's the structure? What is the geometry of water? This is bent, not tetrahedral. Yes, electronic geometry look like tetrahedral, right? But our eyes cannot see the electron. We can see only the bond, right? So it look like bent, right? This is bent. Yeah, we can see this too, our eyes. But if you talk about electronic geometry, yes, this is tetrahedral, right? But molecular geometry is bent. All right. Okay, let's go to the next video.